Okay, shall we get into it?
Yeah.
Alright, so we're doing proposition 6. Let me just rearrange my table here a bit. So, book 2, proposition 6. Okay, I think I need a whole board just for the statement and the diagram. So, if a straight line is cut in half and any straight line is added to it straight on, alright, so here's a straight line, AB. A straight line is added to it straight on, that's BD. Try and make it straight on. D. Then the rectangle contained by the hole with the new line, so that's the rectangle made by AD with BD, plus the square on half of the original line, so let's divide this in half and call that C, is equal to the square on the sum of the half and the straight line being added. Oh yeah, thank you. Half the original line is equal to the square on the sum of such a half and the new line. Alright, so let me construct the diagram. I'm going to be a bit fast with this part because a lot of this is just exactly as what we did last week. So we take AB, we add BD, we cut AB in half. We're considering the rectangle contained by AD and DB. And we're going to compare that to a square, so let me draw the square first. So this is CE FD. This is this part, right? The square on the sum of a half and the new line. They just seem to be almost the same size. That's an accident and a mistake. But that's the square. So that's the thing that we're going to add up these other areas to get. Okay. Yeah, so let me just start with the construction, and again, being a bit quick about it. So I'm going to join DE, draw BG, so this is parallel to those two. And then KM drawn through H. So this is M, this point of this is H, this point of intersection. And then I draw a line through that. Of course I can construct a line here parallel to FD and make it, and then connect this up. Alright, so this is km. I think that's all I need. Yeah. Okay, so now let me make some statements about this configuration. There is one interesting thing here I want to flag, which goes all the way back to proposition 4 of book 1, which I'll get to in a moment. All right, so here's the proof. Since AC is equal to CB, by hypothesis, AL is equal to CH. And this is proposition 1.36. Let's see, so AL, this is kind of a simple point, but I think it's quite fascinating. So AL, where is that? Oh, I missed drawing L, didn't I? This is L. Okay, so AL is this rectangle is equal to HF. Wait, no, that's not the statement I just made. AL is equal to CH, right? Why? Well, they have the same base and their kind of heights are the same, so they're the same. But how does Euclid know that they're the same? That's quite fascinating. So, because remember, being the same, I mean, it's this thing that is kind of what we mean by the same area, but we would look at this and say, well, the area is a product of two numbers, and those two numbers are equal, right? X, y is equal to x prime, y prime, if x is equal to x prime and y is equal to y prime. That is not how Euclid is thinking about it. So if you look at proposition 1.36, what it says, this is the proposition about parallelograms on equal bases going to the same line being equal. I'll just sketch it in and then erase it. But proposition 1.36 is this statement that, which you might remember. So it says if this is equal to this, then this parallelogram is equal to that parallelogram. Now remember what equality means for areas in Euclid. This is like this very interesting sequence of ideas. So equality of area, it goes back from proposition 1.4, which is about triangles with two equal sides and an equal angle between them being the same or being equal. And if you remember, that was the proof of this weird diagram that had this kind of curvy line in it. You remember that one, Ken, where it was like you draw a triangle and then the other diagram has like this thing like this.
Yeah.
Yeah. So, and on that page, there's a little footnote which says, you need a new postulate here. Why? Because the statement is about two triangles. You've got triangle 1 and you've got triangle 2, and they have these sides equal and these sides equal and these angles equal. And the first part of the proof says apply the first figure to the second, which means draw this triangle over there and match that side up with that side. And that gets you to this, and then you show that they're actually coincident figures. Right? So there's this really fundamental role in comparing areas in Euclid. So comparing areas in Euclid really means make a rigid motion with one figure, and then you can fit it into the other figure, or you can cut figures out from each other so that the remainders are equal, like these kinds of operations. But it has this fundamental constituent of moving stuff around and having them lie on top of each other, which is really quite interesting and different to how we think about equality of areas when we're emphasizing numbers. It's kind of like this equality of the areas as a number is like a shadow of this more primitive equality that happens with the transformations. Yeah, so this equality that is in proposition 1.36 goes through 1.4 to 1.35, which is this same statement, but with the parallelograms actually the same. The base is actually the same line, not just equal. And then you get 1.36, which is what I sketched above. But all of that is lying behind this very innocuous statement, which we take at face value, that AL is equal to CH. So I think that's, like, the equality of areas is much less primitive in Euclid than it is for us when we work algebraically. And that's part of the reason why it's so much more cumbersome to do what they're doing here, right? So yeah, I thought that was interesting. In any case, AL is equal to CH, but CH is equal to HF. That's by 1.43. Let me see, why is that? That's the opposite parallelograms, opposite the diagonal inside a parallelogram are equal. We talked about that last time, right? So here's a parallelogram, here's a diagonal, and then we have these two parallelograms on opposite sides, and they're equal by that proposition. So CH is equal to HF, so AL equals HF. Add CM to both. Okay, so AL plus CM. This shows AM is equal to CH, what did I say? AL equals HF. Right, and then I'm adding CM to both. So that's the gnomon, right? Did we talk about the gnomon last time, or is this the first time it's appearing? I forgot.
Yeah, we talked about it last time.
Yeah, okay.
Yeah.
So this area here, where you kind of color in three parts of a division of a parallelogram along a diagonal like this, this is the gnomon, and that is CM plus HF. Right? I guess let's label it in here. So NOP. It's kind of interesting. This is a new naming convention for a sequence of figures where you use the intersections with some of the parts. So that seems to be how this works. But AM is the rectangle, yeah, right. But AM is the rectangle contained by AD and DB. Let LG be added to both. So if we add it to the gnomon, then we get the square on CD is equal to AM plus that square on LG.
How do you have a rectangle contained by AD and DB?
Yeah, right. That's kind of a terminology. There is no rectangle that is sort of literally contained by those two, but what Euclid means by that phrase contained, which is a technical term, is take those two lines and construct a rectangle which has lines equal to those as its sides.
Oh, okay.
And I guess I didn't say it out loud, but so AK is equal to BD.
Gotcha.
Yeah, that's because it's equal to BH, and that's a square from sort of same argument as last time. Yeah, but thanks. So that's... are we done? Let me see. Then the rectangle combined by the whole with the new line, so that's ADBD, which is AM, plus the square on half of the original line, which is LG, is equal to the square on the sum of such a half in the new line, which is the square on CD. So yeah, we're done. That's what we needed to show. All right. Any questions about that one? So yeah, really no new ideas there. That was like a slight variation on the previous proposition. And to be honest, when you look at this, the footnotes in Heath's treatment of Euclid, where it gives the equivalent algebraic formula, I won't reproduce it because I don't know that it adds much, but this part seems very torturous, right? It's like we're going to do 6 variations on this same thing in order to capture, some slight differences in the algebra, which we would not bother to write down as separate identities. I guess it's tempting just to think, the ancients were stupid. I'm inclined to maybe throw them a bone a little bit and attribute it to this difference I was talking about earlier, where actually what they're doing is harder, right? It is harder to prove these identities. Not only harder, but you're actually proving more because you have a more restrictive notion of equality and sum when you're doing it in terms of geometric figures. So actually these algebraic identities, I think, are strictly weaker objects. And so they have to work harder, and it's somewhat more cumbersome because I think they're proving more.
So here's a question. What can, using Euclid's postulates, you can probably translate some of these operations that we're doing in algebraic terms. Are there reasons why, are there algebraic manipulations that we do to go between some of these identities that they present, that the translator presents, to go between them? Are there manipulations that are not allowed geometrically? That's why they're having to reprove a lot of these identities. Like we would just manipulate these. But I tried to do this in proposition 1 and 2, and I realized, maybe this is not the spirit of Euclid. If we just kind of say, well, this is just the algebra, and then we can just move these terms around. I wonder if there's some operations that allow, like subtraction.
Yeah, I was about to say that. Yeah, I think that's right. Maybe we should think about it more carefully, but my suspicion is that it's subtraction that's the problem. So it would, in order to subtract, you somehow have to embed the things you want to manipulate algebraically into a larger object from which you can subtract bits.
Right.
So actually moving a term from one side of the equality to other is a whole ordeal for Euclid.
Yeah. So maybe last week when I talked about the nomen, I kind of wrote it notationally as the big square minus the little square. Maybe that's also not in the spirit of Euclid either, and maybe that's why he does the whole NOP thing that you're doing there, right? Going around the central point where all the lines intersect, rather than we're going to take the square and just knock out the smaller, or take a parallelogram, knock out the smaller one, right? So maybe subtraction is not something they're thinking of doing. But they do cut pieces of geometrical objects and add it to another one. And the action of cutting an object into two, removing one part, that seems to be subtraction to me, though, right? I don't know.
Yeah, but it's a very restricted form of subtraction, right? Because somehow he'll only do that if the resulting figure can be decomposed. Somehow, like in this case, you draw the line DE, and then you've divided it into two pieces, and you can kind of identify some piece inside it that's the difference. But there's only a very limited set of things you can subtract this way, whereas algebraically, anything we could write down, we'd be happy to subtract from something else, right?
Right. And we can, use integers and multiply by things, right? I don't know whether Euclid is so free with just dividing or multiplying. It's certainly not dividing, unless you can construct it somehow, right? I've seen him multiply things by 2, but that's usually because you've got overlapping figures, right? And so now you've got 2 of these. It's not like I'm just going to produce another instance of this out of thin air, and now I have 2 of them. Yeah, so I guess we can do the next proposition next week. We've got like 4 minutes left.
Yeah, I think that makes sense.
But it's very similar to, in spirit, to the ones that came before, right? The constructions are essentially the same as what you've done this week and what I did last week. Make a square, draw a diagonal, consider parallelograms, match up areas.
Yeah. Yeah, I looked a bit forward in book 2, and it seems clear that just like Pythagoras' theorem was the culmination of book 1, that the cosine formula is the culmination of book 2, which makes sense, right? It's the generalization of Pythagoras' formula to a triangle that's not a right angle.
Right.
So it's that's where we're going. So I think that should be cool.
Cool. Awesome.
Yeah, I do like this process of thinking carefully about what subtraction means and thinking about it in terms of geometric figures rather than numbers, because it's of course in algebraic geometry, when we talk about the Grothendieck group of varieties, for example, we're doing exactly this, right? It's
Right.
and then there's a map from that perhaps to numbers, right? But somehow there's a lot of, probably the people who thought first about the Grothendieck group of varieties, maybe indirectly were inspired by what Euclid is doing here. But I really mean it when I say that there's something actually more subtle, more interesting, and more deep about what Euclid is doing with areas than what we do with numbers. It's not stupid. Yeah. There's actually more there, and that's, for example, in algebraic geometry, what we mean by studying the Grothendieck group of varieties, and then also looking at kind of group homomorphisms from that to simpler things. But there's more information in that Grothendieck group. Now, in this case, maybe, I don't know what the set of figures modulo these relations are. It may just be literally, the rational numbers or something. So maybe there's no more technically to it. But I do think it's one of the reasons to pay attention to Euclid and some of these older works is that the genesis of deep ideas lies in these distinctions, and because we came so late in this historical process and we already had the algebra and we already had the numbers, we maybe don't properly get what the depth of the old idea was.
Did we scare off everybody by mentioning Grothendieck groups?
No, Ethan always has to go at exactly the hour. So.
Oh, okay, fair enough.